How do classification algorithms enable BCI communication? Imagine being able to send messages or control devices just by thinking about it. That's what brain-computer interface communication aims to do. It turns brain signals into commands that computers can understand. But how does this process actually work? Let's break it down. First, the brain produces electrical signals that are recorded using devices like electroencephalography or EEG. These signals are very complex and contain a lot of noise, making them hard to interpret directly. That's where classification algorithms come into play. They help make sense of these signals by finding patterns that match specific thoughts or intentions. The process starts with feature extraction. This step pulls out important parts of the brain signals, like certain wave patterns or frequencies that relate to different mental tasks. For example, imagining moving your hand or focusing on a flashing light creates distinct brain activity. These features are what the algorithms analyze to tell what the person is trying to communicate. Next, the system needs to learn how to recognize these features. During training, the algorithm looks at many examples of brain signals linked to known commands. It learns to associate certain patterns with specific actions, like selecting a letter or moving a cursor. This training process helps the system become more accurate over time. There are several types of classification algorithms used in BCI communication. Linear Discriminant Analysis finds the best way to separate different mental states by drawing a straight line through the data. Support vector machines look for the boundary that best divides different classes in a high-dimensional space. K-nearest neighbors classifies signals based on what the closest examples are labeled as. Decision trees and naive Bayes use rules or probabilities to decide what the signals mean. More advanced models like deep neural networks and convolutional neural networks can learn very complex patterns, improving accuracy especially with large datasets. These algorithms are chosen based on how accurate they are, how fast they work, and how much computing power they need. Sometimes, combining different algorithms creates a hybrid system that works even better. This flexibility allows BCI systems to adapt to different users and tasks. In real-world use, classification algorithms help people with severe motor impairments, such as those with amyotrophic lateral sclerosis, to communicate. They can control a computer cursor, select letters, or operate robotic limbs just by imagining specific movements or focusing on visual cues. For example, a person might imagine moving their hand to move a cursor on a screen, and the system recognizes this intention through the pattern of brain activity. Recent improvements include integrating language models with classifiers. These models help predict words or correct errors, making communication faster and more natural. They reduce the mental effort needed from the user and improve overall performance. So, in simple terms, classification algorithms act like a translator. They take the raw, noisy signals from the brain and turn them into clear commands. This technology opens up new ways for people to connect and interact using only their thoughts.